All right. Today we are going to look over some dipole moment and then do a little bit of delta H calculation. Won't take us long. It's a pretty light day in order to give us time to get your test back today. So dipole moment is basically a visual representation using an arrow showing where electrons in a molecule itself actually reside. There's a difference between molecular polarity and bond polarity. You can have a molecule with polar bonds, but the whole molecule itself be nonpolar. And so what the dipole moment arrow tells us is what's going on with that electron distribution. So if you look at this, here we have a structure. Today I'm going to be drawing some Lewis dot structures. Don't panic if you don't remember how to do them, because that's what we're doing tomorrow. So you're going to have to do dipole moments on Lewis dot structures that you will eventually be able to draw again. Really quickly tomorrow you'll be able to draw them. But here we have water, and you can see that water within itself, and I don't want you to think the arrows I'm drawing now are dipole moment, but we know that oxygen is more electronegative than hydrogen. So within the bonds, the electrons are being pulled in that direction. And due to the fact there's a lone pair here, which is forcing this bent shape, the majority of our electrons are in the area of the hydrogen. Okay? So as far as what to draw for a dipole moment, here they drew the arrow actually on the molecule. I'm not a fan of that. I would rather you just go ahead and draw it like right under or on top of the molecule itself. The overall molecule then is polar, and you're going to draw an arrow toward where the electrons are, and then a little hash mark at the back end. That indicates a dipole moment. And then you're going to label partially negative or partially positive. This side of the molecule is partially positive, and this side is partially negative. So the arrow always goes in the direction of the more electronegative side of the polar molecule. So here, this is just a really cool, that we use these pictures a lot in organic chemistry because we really care about where electrons are in organic. And you can see that red is a high concentration of electrons, and it graduates down to blue, where blue is the lowest concentration of electrons. So you can see here clearly that that is obviously a polar molecule. One side is definitely more concentrated with electrons than the other. Okay? So when we see this next one is CO2. Now, CO2 is an example of a nonpolar molecule, but the bonds themselves are polar. Due to the fact that these are 180 degrees apart, and there is an even distribution of electrons throughout, that makes it nonpolar. So, is there a dipole moment? No. So there is no dipole moment in nonpolar molecules. So I don't want to see any arrows. Now I know on the picture they have this and this. They're showing that they cancel each other out, but when we're drawing dipole moments, I want you to draw an overall dipole moment. This does not have one. So if you look at this picture, do you see how evenly distributed the electrons are? With equal amounts of red, yellow, green, all the way to the middle. Okay? So that makes that a nonpolar molecule. Okay, for these, we're going to draw the Lewis structures again. Don't worry about that. Tomorrow is the day we relearn these. So HI is H attracted to I. Now, it's hard to tell from the trend itself, but if you were to look back at the electronegativity values, I is definitely more electronegative than hydrogen. All your halogens are going to be more electronegative than hydrogen. Okay? And that's, if you think about it, these are acids. And what do acids do to protons? Acids are proton donors. They donate protons. So because of the ability to donate that proton, it means those halogens are hanging on to the electrons in the acids. So these halogens are definitely more electronegative. So if we were to draw a dipole moment here, we're going to point toward the I, because that's more electronegative with the little hash mark. And then this is partially, what's I? Negative, and this guy is partially positive. It's pretty simple. Okay, B is a triple bond N, and you'll learn how to do that again tomorrow. Is there a dipole moment on this one? Why not? Nonpolar. Yeah. In the case where we have a diatomic molecule, the bond polarity is actually equal to the molecular polarity because there's just two things there. And they have equal electronegativity, so not polar, so we don't draw a dipole moment. And this last one, we've got 2 chlorines and 2 fluorines around a carbon. Now, normally I'm going to say it doesn't matter where you draw your groups attached, because I'm going to show you a 3-dimensional molecule now why it doesn't matter. What shape is this? 4 areas. Who remembers? 4 areas around a central atom. What's the shape? Tetrahedral. So if you look the way this looks, it really doesn't matter where you put the chlorines and fluorines. Like you could do a chlorine and a chlorine on top and bottom and the fluorines on the side. In terms of what it looks like in 3-dimensional space, it really doesn't matter. If the blues on this model are fluorines, and I put it here and here, they're still next to each other. If I put it here and here, they're still next to each other. If I put them here and here, they're still next to each other. So no matter where you place them on the 3-dimensional object, your fluorines are going to kind of be on one side and your chlorines on the other. That's just how the 3-dimensional 109.5 works. So to make my point here, I'm purposely putting them next to each other just so I can make an arrow going in just one direction. So what's more electronegative, fluorine or chlorine? Chlorine. No, fluorine. Fluorine is the most electronegative element. So the electrons are, in general, being skewed toward the fluorines. Now don't draw these, but each of these bonds is polar toward the halogen, but the F's are more polar and more electron withdrawing. So that makes the entire dipole moment go toward the fluorines. And that's what I'd want to see. So knowing what was coming, I purposefully drew my CLs on one side and my F's on the other. But in 3-dimensional space, like I said, it doesn't matter where you put them. They're always going to be next to each other. Does that make sense? If not, you can look at this more closely after lecture. Okay, so what side of the molecule? So if we had the rainbow thingy from above, our red would be on the fluorine side. This side would be more red, and this side would be a little more blue. And so this is partially negative, and this one is partially positive. Okay? So that's all we're going to talk about polarity. We'll hit all this again when we do the VSEPR chart, and you have to tell me if something's polar or nonpolar based on the Lewis dot. So what we're going to do right now is look at bond energy. So the textbook puts bond energy in this chapter. I go back and forth. I really feel like we should be putting this in thermo, but they put it in this chapter because it's about energy of a bond. But I don't think you need to know energy of a bond to do these calculations. So this is yet another way to find delta H of a reaction. Let's go back in our head. What were the different ways to find delta H that we did? There are Big Mama, Flippy Thing. What'd you say? Calorimetry and the stoic. Very good. Calorimetry and stoic. Those were our ways of finding delta H. Today we're going to add this 5th way, and it's by the use of bond energy. Bond energy is found by a modified Big Mama. And it's going to look like you're doing it backwards, but you're not. And I'll try to explain why, but sometimes in the explanation it gets even more confusing. So what I want you to know first and foremost is you do bonds broken minus bonds formed. Bonds broken minus bonds formed. What's happening here? It looks like we're doing reactants minus products, right? Because we break the reactants and we form the products. We're really not, because what bonds broken minus bonds formed do is allows us to not have to change the signs. If we were going to use Big Mama on this, we would have to decide, okay, if I break a bond, that means I'm putting energy in. Those are going to be positive values. So I'd leave my bond values positive. If a bond forms, energy is released, and I'd have to then make all those negative. So in lieu of us having to do those sign changes, it's been modified to just use all the positive values of the delta H's and just do bonds broken minus bonds formed. So that's all you need to remember. Bonds broken minus bonds formed. So let's go ahead and do, it's actually one on this page. We're going to do this problem. Now, I'm going to do it. It's not going to be the long way, but you're going to be like, did you have to break all those? No, you're going to figure out your own methodology as you learn this. Right now, I'm going to break every single bond and then form every single bond and do the calculations accordingly. So this molecule right here, it's a C with 3 H's attached, and then a C is attached to an N, and then the N is triple bonded to a C. And that's going to, I don't know why I just did an equilibrium sign, whatever. Then we've got a C attached to 3 H's. This time the C is attached to a C, and then we have a triple bond to an N. Now you can pick and choose what bonds, but right now I just want to break everything so you can see. In order to break all these bonds, I'm going to break 3 of what? H to C's, right? Y'all see 3 H to C's? And then how many C to N's am I going to break? 1 C to N single bond, but it has a different value than a C to N triple bond, which I'm going to break as well. So those are all the bonds I'm going to break. Bonds broken minus bonds formed. So what am I forming? 3 H to C's, and then I'm forming 1 C to C, and then I'm forming 1 C to triple bond N. So the math is 3 times H to C is 413 kilojoules. I'm just taking it from this table. 1 times C to N is 305. 1 times C triple bond is 891. That's bonds broken. These are, you add those up. Minus, this is the sum of the bonds broken. 3 times H to C is 413. 1 times C to C is 347. And then C to N is 891. Now, if you look, you see how you could have avoided some of these? We could have gotten rid of that. You can get rid of that if you want, and then just do this. But I wanted you to be able to see that before I started telling you not to write things down. So bonds broken minus bonds formed, because this minus this is 0, that minus that is 0. Does everyone get that? All right, so what is our delta H of the whole reaction then? Negative 42 kilojoules per mole. And it makes sense. If you break every bond and then reform every bond, whatever energy is extra or whatever energy is missing is what we're actually calculating, which is the delta H of the reaction. How much is absorbed or how much is released, and this is going to be an exothermic reaction. So this is the exact same delta H as we did before. If they just gave us heats of formation, what if they just gave us heats of formation of that one and that one? How would we find delta H? Big Mama, right. So again, many different ways to solve for delta H. Whenever they give you bond energies, though, this is the way to do it. Yeah. For this test, right, but on the final it's gonna everything, yeah. Right, and any free response that we have for practice, for extra credit could be anything. All right, so we're going to now look at this. This is your bond energy table. Notice that all the bond energies listed are positive, okay? It's listed as the energy required to break a bond. There was a problem not too long ago on the AP where students were asked to calculate the bond energy of a particular bond, and they didn't have, we're going to do one of those, but it didn't have it on the table. And most students, not knowing to do broken minus form, did Big Mama. So a bunch of them got negative values. I need you guys to be paying attention to things. If you were given a bond energy table, it's obvious they're all positive. And if on your test you got a negative bond energy, that should be a red flag to you that something's wrong, because obviously bond energies are positive, okay? So watch out for stuff like that. The only thing on this table to watch out for is this little asterisk here. This C double bond O is the carbonyl group. Normally in compounds, all your organic compounds and stuff, it's 745. However, if you're looking at the C double bond O in specifically CO2, you're supposed to use 799. So just watch that. Okay, so let's do this. Bonds broken. What are we breaking here? 4 C to H's. What's the value from your table of that? 413. Plus, how many double bond O's are we breaking? 2 O to O's. And what's that value? 146? 495. Okay, that's bonds broken minus, now what are we forming? Carbon dioxide. Be careful, that's the 799 one, right? So how many C to O's at 799? 2 at 799. Plus, how many H's are we breaking? How many H's? 4 H's, right? Each has 2 H's, and there's 2 of them, so we're breaking 4 H's. Okay, so let's go ahead and calculate the delta H for that. Bonds broken minus bonds formed. I'm sorry, I couldn't hear you. Did anyone else get that? Okay, cool. Now, this is different. Today, I just changed this problem this morning, so your next in-class problem is different. So I want you to write down the new problem. It says the delta H for the reaction below is negative 109 kilojoules per mole. Knowing the bond energy for N triple bond is 941 and H to H is 432, calculate the bond energy for one N to H bond. Now, I know you can look at your table and get it. That's not the point. You're not going to have that information if you get a question like this on the AP. So they'll give you a table leaving out the one bond that you need. So any ideas of how we're going to approach this? Set up algebra. Okay, good. What are we going to do? Naira? Exactly. You know the delta H of the reaction is negative 109. So negative 109 is going to be equal to broken minus formed. You know the H to H, you know the N to N, and we're going to leave our unknown as the N to H bonds. Does that make sense? So let's do that. We're going to say negative 109 kilojoules per mole is equal to, bonds broken, we're breaking 1 N triple bond N, which is 941, plus 3 H to H's at 432, minus, how many N to H's am I forming in ammonia? It looks like this, a lone pair. Right, where'd you get 6? Because I've got 2 ammonias, right? So 6 and X is what we're looking for. Make sense? So let's go ahead and calculate that. Now, this is where students messed up. They did products minus reactants, so they got the right answer, but it was the wrong sign. And so rather than paying attention to the entire table's positive, so it must be positive, they just said, oh, it's a negative, and they didn't get credit for it. Because it was only a 1 point given. So the N to H bond energy is equal to 391. Now, just for grins, what is it on the table? Yeah, isn't that convenient? Okay. This last one is a contest. Whoever runs to me with the correct answer on their paper first gets a sticker. Go. It's a a lot of people miss this one because there's a lot of numbers to look at. Sorry, people at home. I can sing you a song at home while people are working. Actually, everyone close your eyes. I'm going to end the video. Nobody look up. People at home, the answer to this problem is the following. So, after doing bonds broken minus formed, this is the number that you should get. All right, that's the end of the video. Bye.